Okay, we're going to talk about infinite limits. So basically, most of your answers to the limit questions in this section are either going to be infinity or negative infinity. So I want you to consider the function 3 over x minus 2, and I've graphed it for you over here. Where is there an asymptote on this graph? X equal 2 or y equal 2? Yeah, x equal 2. Unfortunately, my graph program won't draw in the asymptotes. But y'all didn't need it, because you knew it. All right, from the graph and or a table in your calculator, as x approaches 2 from the left side, what are the y values approaching? Negative infinity. And as x approaches 2 from the right side, f of x is approaching infinity. So this behavior is denoted as a limit. So the limit as x approaches 2 from the, what's the first one? Is that left? Left is what? Negative infinity. And as x approaches 2 from the right, it's a positive infinity. So a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. If your y values are approaching infinity or negative infinity, it's considered an infinite limit. All right, now, once again, be sure you recognize that the equal sign in the statement limit of f of x equals infinity, it does not mean that the limit exists. We're just being a little bit more specific about why it's failing to exist. All right, so determine the limit of each function as x approaches 1 from the left and from the right. We're going to use our calculator for this. Okay, so there's my function. I could graph this if I want, but I want to have a little bit of practice using the table with these infinite limits. So I want to start my table at x equal 1 because that is where x is approaching. And I am going to leave my delta table as 0.001. Okay, so the limit as x approaches 1 from the left, is that coming down from the top or up from the bottom? Down from the top. Good. I'm going negative 500 and then negative 1,000, so is the limit negative 2,000? It's negative infinity. When you're jumping, when these y values are jumping up by a big, big number, your limit's going to be either infinity or negative infinity. And the limit as x approaches 1 from the right side is going to be positive infinity. Good. Okay, do part B on your own. You could just say limit 1 as x approaches 1 from the left equals negative infinity, and limit as x approaches 1 from the right equals positive infinity. Or you could just write left, negative infinity, right, positive infinity. We'll do that on part B. And we'll just do L and R. I'm all about being lazy, if it's appropriate. Okay, what'd you get for the left limit? Both are positive infinity? Okay, good. All right, C and D, I already gave the graph to you. So on C, as x approaches 1 from the left, infinity from the right, negative infinity. D, negative infinity, negative infinity. All right, if f of x approaches infinity or negative infinity, as x approaches some specific number from the left or the right, then the line x equals c is what? What type of asymptote? Vertical asymptote. Good. So you've learned about vertical asymptotes for a really long time, but it's very closely tied with limits. All right, we're going to find all of the vertical asymptotes. What creates a vertical asymptote in a graph? 0 on the bottom of a fraction. So what's the easiest way to find the zeros of the bottom of a fraction? Okay, set it equal to 0. I need to hear that F word, factor. Okay, just a couple of you chuckled. What's wrong with y'all? Okay, that's better. Okay, I tend to just factor the bottom part. So what does x squared minus 1 factor into? Yeah. X plus 1, x minus 1. So how many vertical asymptotes do you think we're going to have? 2. One at x equal negative 1 and one at x equal positive 1. My only hesitation with you setting or the bottom equal to 0 is that if some of you, if you set x squared minus 1 equal to 0, then you're going to get x squared equals 1. And when you take the square root of both sides, you get x equals 1. And what did you forget to do? Plus or minus, right. So if you're good about doing plus or minus when you take the square root of both sides, I'm okay with that. But otherwise, it's probably better to factor. All right, on B, how does the bottom factor? It doesn't in the real number system. And the good news about calculus is that we don't have any imaginary numbers. We only deal with real numbers in calculus. So there are no vertical asymptotes here. All right, f of x equals cotangent x. There's no denominator, so where are those? Okay. Cotangent of x can be written as cosine x over sine x. Good. So my asymptotes are where the sine of x equals 0. And I heard somebody say OIO chart. What are two values that have an angle? Okay. So x equals 0 and x equals pi. Are those the only two values? Yeah, it'd be 0 and then every period, which is 2 pi n, and pi plus 2 pi n. So I could write it like that, or because we're in BC calculus, maybe we could condense that into just one equation. Yep, either 0 plus pi n or just pi n. Good. Um, 0 plus 2 pi n is going to give you 0, 2 pi, 4 pi, 6 pi. But pi plus 2n is going to give you pi, 3 pi, 5 pi, 7 pi. So if you kind of squish the two together, it's really just happening every pi. All right, find your vertical asymptotes on part D. How many vertical asymptotes does this one have? I was waiting for someone to say, what? There's just one, because when you factor the bottom, you do get two factors. But if you factor the top, one of those factors on the bottom is the same as the top. So at x equal negative 5, we actually have a whole. So the only vertical asymptote is at x equal negative 2. All right, a vertical asymptote is called a non-removable discontinuity because there's nothing that you can do about a vertical asymptote. You can't take that asymptote out. But a whole is a removable discontinuity because basically you can plug up a hole. So let's take the function x squared minus 9 over x plus 3. Graph that for me without your calculator. Well, what do you need to do to graph it? Factor. There's that F word again. The math F word is okay. Okay, there's my graph. Everybody cool with that? The whole, no, the whole's at -3, -6. It's kind of like they say in geometry that it's not drawn to scale. All right, so I have a hole in this graph. The reason that this is called a removable discontinuity is I can say, all right, well, therefore, I want f of x to equal x squared minus 9 over x plus 3 whenever x does not equal -3, but I want for f of x to equal -6 when x equals -3. So what that does, so now I can just fill in the hole, and I no longer have a discontinuity. I've removed it. So the reason it's called a removable discontinuity is you can redefine the function to exist at that hole using a piecewise function. Okay, the reason that you can't do that with the asymptote, well, you could still put a hole, or I'm sorry, you could still put a dot on top of an asymptote, and it would make the domain all real numbers, but it wouldn't make it, it would still not make it a continuous function. So the difference is defining the whole domain and having a continuous function. That's a good question. All right, last problem. I determine whether the function has a vertical asymptote or a removable discontinuity at x equal 2. Now, a removable discontinuity is a hole. I don't care which notation you use, as long as when I use either one, you know the difference, or that removable and hole are the same thing. All right, so what do you think? Anyone figured this out? It's a hole. So the x minus 2's cancel, so there's a hole or a removable discontinuity at x equal 2. Very good. Congratulations, you've finished the first chapter of calculus.